Welcome to lecture 2.7 on related rates. This is actually one of my favorite topics in calculus, and for me it connects all the dots, or it connects a lot of the dots, maybe not all the dots. And it's also very intuitive with the way the world works, okay? So let's look at this. Notice if we pump air into a balloon, it says a spherical balloon, that as we pump air into it, the volume of the air inside the balloon is increasing, but also the radius is increasing, okay? And the rates of change, you know, the rate of increase of the volume and the rate of increase of the radius are both related to each other. In general, it's much easier to measure the rate of increase of the volume. We could calculate with some instrument how much air we're pumping in per minute, per second, than it is to actually calculate the rate of increase of the radius. We don't really have a good way of, we could do the circumference, measure that, but that's going to take a lot more time and energy. So often this is very true as well, that one rate of change is easier to measure or to calculate than the other. And so in related rate problems, the idea is to compute the rate of change of one quantity in terms of the rate of change of another quantity, which is usually more easily related. So here we could, if we figured out how the volume was increasing, we could then use a formula to figure out how fast the radius is increasing as that volume is increasing at a certain rate. And so this is the idea of related rates, that the volume is related to the radius. And we know that because the volume of a sphere depends upon the radius, right? When we're trying to find the volume of a sphere, 4 pi r cubed, I believe. So to do this, we find an equation that relates both quantities, which I just gave you, and then we differentiate both sides using the chain rule with respect to time. Now remember, what we're talking about here is using implicit differentiation, and that's what it is talking about when it's talking about the chain rule. Remember that when we were differentiating a y term, we first differentiated with respect to y and then wrote y prime, and that was an example of the chain rule, right? The outer being the y function and the inner being the derivative with respect to x. Okay? So let's see what happens now. Alright, let's look at an example. So air is being pumped into a spherical balloon so that its volume increases at a rate of 100 centimeters cubed, or cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? Okay, so it's a good idea to identify what's given and what's unknown. Okay, so to go through the problem and figure out what are we looking for and what do we know. Okay, so in this problem, if we make V volume and R radius, what do we know and what are we seeking? Let's go back one step by time. Excuse me. Let's go through the problem and look for numbers. Its volume is increasing at a rate of 100 cubic centimeters per second. So what is that telling us? Is that the volume? No. It's telling us it's the volume is increasing at that rate. So this is a rate of change. Now when you're identifying pieces of given and what we're looking for, use the notation that we're familiar with. What do we use for the rate of change? This is in centimeters per second. It's the rate of change of the volume. So this is dV dt. The derivative of the volume with respect to time is 100 cubic centimeters per second. It's asking us how fast is the radius of the balloon increasing, and so we're trying to figure out the derivative of the radius with respect to time, and when the diameter is equal to 50. Now that's, so our diameter is equal to 50. That's not either of our variables that we've already identified that we're talking about, volume and radius, but hopefully you know that the diameter is equal to 2 radius, so our radius, when the diameter is 50, our radius would be 25. Okay, so the next thing we want to do is identify an equation that relates the two quantities. We're talking about the volume of a sphere and the radius. Well, the volume of a sphere is calculated from the radius, and the volume of any sphere is equal to 4/3 pi r cubed. Okay? So now we differentiate each side with respect to time. So on the left we get dv dt. Hey, look at that. That was actually a given in the problem. And that equals, again, here on the right side we're going to do the implicit differentiation. Because our variable here, we're looking for dr dt, but we have we can take the derivative of this equation with respect to r and then do the dr dt. Again, this is the chain rule or implicit differentiation. So if we're trying to find dr dt, notice what we're doing is we're taking the derivative with respect to time of both sides. And on this side, we'd first take the derivative with respect to r, and then the derivative of r with respect to t. Okay? And since this equation is equal to volume, I just use that notation here. So now let's plug in what we know. So dv dt is 100. That was given in the problem. dr dt is what we're looking for. And dv dr is simply the derivative of this function with respect to r. Bring the 3 down in front, so 3 times 4/3 is 4. Pi is a constant, r squared. So this piece here is just simply taking the derivative with respect to r. Might have been easier if I had wrote d over dr and then the formula times dr dt. But hopefully you can see that. And remember, once we do that with implicit differentiation, what we do is we solve for what we're looking for. And in this case, we're looking for the rate of change of the radius with respect to time. So I divide both sides by 4 pi r squared, which gives me 25 over pi r squared. And remember that we said the diameter is 50, so our radius is 25. And so I get 1 over 25 pi, or 0.127 centimeters per second. Okay? Now I like these because I feel like they give you examples that are maybe not true to life, where you don't really care that much about how much air is in a balloon, unless maybe you're flying in one. But at least it kind of hopefully brings it a little bit closer to reality than just differentiating formulas. So we can see that we can actually calculate how fast the radius is changing with respect to the volume in this problem using our calculus and implicit differentiation. So let's look at another problem. A ladder 10 foot long rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 feet per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? Okay, so one of the things I caution all of my math students about is word problems that if you read it from beginning to end, the majority of word problems are overwhelming with the data, and it's very confusing when you just read it through like a story. Okay, so one of the things I recommend is that you build your picture. In this case, we have a ladder leaning against a wall. I can pretty simply build that picture. Okay, so I have a ladder leaning against a wall. The blue is my ladder. Okay, so I've already taken care of the first sentence, and if I add a 10 right here on the blue ladder, I've already started filling in some of my information. Okay, so the ladder is 10 feet long. It's sliding away from the wall. It's sliding away from the wall, so my ladder is going this way. Follow my little arrow there at 1 feet per second. How fast is the top of the ladder sliding down the wall when the ladder is 6 feet from the wall? So when this distance is 6 feet. Okay. Now, one of the things that you want to think about when you're talking about these rate of changes is the polarity of them. Are they positive or negative? And so a good rule of thumb is if the ladder is sliding away from the wall at 1 feet per second, is this distance growing or shrinking? When the ladder is sliding away, is the distance from the wall growing or shrinking? It's growing, right? Because we're getting further and further away from the wall as the ladder slides away. So we're looking for how fast the ladder is dropping down the wall. And notice that this distance is negative because it's getting smaller. As the ladder slides down, the distance from the ground is going to get smaller. So we expect this derivative to be negative. So derivatives that are positive are increasing. Derivatives that are negative are decreasing. Okay? So our question is, again, if we think of this in terms of x and y, that's what I've done here. I've used dx dt because this is, if you think of this, of the bottom line, the ground as the x-axis, you can think of the edge of the wall as the y-axis. So I often recommend using variables with letters that are related, but in this case, I guess I could have used dg dt, the distance from the ground, and maybe d wall dt, or I could have used ground and height, or it doesn't matter, but here I used it because it's almost like a Cartesian system. I used x and y. Okay, so I have all of my values here. Now remember, I have to figure out a formula about these three, or in this case, these three areas. I've got the distance from the wall, I've got the height along the wall, and then I've got the ladder itself. And hopefully, looking at this, you can see that what we have is a triangle, and it is a right triangle, so we can use Pythagorean's theorem. Okay, we can use Pythagorean's theorem, and so x squared, the distance from the wall, plus y squared is going to equal our hypotenuse square, and our ladder, the length of our ladder is not going to change. It's always going to be 10. So I get x squared plus y squared equals 10 squared, or 100. Okay? Once I have my formula, remember with related rates, what we do is we differentiate each side with respect to time. Since I'm taking the derivative with respect to time, notice now I have two implicit differentiations. So when I differentiate x, I get 2x, but because I'm differentiating with respect to time, I have to add x prime or dx dt. When I differentiate y squared, I get 2y. That's the differential with respect to y. But again, I'm looking for with respect to t, so I also get dy dt. On the right side, the derivative of a constant is always equal to 0. So now I have these values. I know what my x value is, so I can plug that in. I was given dx dt, so I can plug this in. I don't know what y is, and I'm trying to find dy dt. So we've got a few more things to figure out. So the first thing I want to do is figure out what is y. Well, remember, we can go back to this equation that these three quantities, by Pythagorean's theorem, are always connected to each other. So if I plug in x equals 6, which is the value we're looking for, I get 6 squared plus y squared equals 100. So I can, if I calculate that out, I'm going to get y squared equals 64, or y equals 8. So now I can plug in all these values and find out, and then solve for dy dt. X is 6. That's when the ladder is 6 feet from the wall. Dx dt is 1 feet per second. That was given to us in the problem. 2. Y, we just calculated using Pythagorean's theorem. 6 squared plus y squared equals 100. And dy dt is what we're actually trying to solve for. So now I have a very simple algebraic equation, and I get, if I solve for dy dt, I get 12 plus 16 dy dt, and then I solve for it, I get negative 12/16, or negative 3/4 feet per second. And again, you can even see here that the sign is what we expected it to be. It's actually shrinking, so we expect the sign to be negative. So this is an interesting problem. I like this problem because it's simple. When you read it, it's very complex, but when you look at it, you realize we're just dealing with a triangle, some basic formulas of Pythagoras, and then some good insights into rates of change. Remember, if the whatever you're measuring is shrinking, it's a negative. If it's expanding or increasing, it's a positive. So it will help you kind of label the polarity of your variables and the different notations. Okay, so again, drawing in this case, Go back and label your parts using calculus notation, especially important for the rates of change. That will help you solve these problems. Find a formula that connects the two quantities. Differentiate each side with respect to time, being very careful. In a lot of these related rates, even the x variable will be implicit differentiation. Plug in your values and then solve. All right, let's try another one. A man walks along a straight path at a speed of 4 feet per second. Alrighty, we can see we've got a derivative there. A searchlight is located on the ground 20 feet from the path and is kept focused on the man. At what rate is the searchlight rotating when the man is 15 feet from the path, from a point on the path closest to the searchlight? Alright. So, again, we've got a lot of stuff in here. When I read that as a story from beginning to end, it becomes quite confusing. But I can draw this pretty simple. So first I have a straight line. So a man walking on a straight line. Next I have a searchlight located on the ground 20 feet from the path. So I've got my straight line, which is my path. Somewhere out here, 20 feet directly from there, perpendicular to there, I'm going to have the searchlight. And it's going to rotate focused on the man. At what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? Okay, so again, I've got the searchlight 20 feet from the line, and then the man is going to be 15 feet down for the point we're looking at. And so I can visualize now, even though I just kind of did some squigglies here with my arrow, I can visualize again that what I have is a triangle. Again, my straight path, my searchlight 20 feet away from the path, which is perpendicular. The man is going along this, and we want this when x equals 15, when he's 15 feet away. And it's asking what rate is the searchlight rotating? Well, that's an angular measure, so we're going to have to use some trig here, okay? So we're given this value, we're given this value, so what do I know about opposite and adjacent? Which trig function deals with opposite and adjacent? Notice we don't have the hypotenuse, although we could find it, but that's also going to be changing at all times. All right. Sorry, excuse me. Given my diagram here, let's label the parts. So the man's walking along a straight path at 4 feet per second. So that's my x value labeled in my diagram. Is it positive or negative? Given that it's increasing, it should be positive. Okay? The light is rotating. Oops, in my diagram we can see that's the theta. Is the angle, we're trying to find the rate it's changing, and is it going to be growing or shrinking? What do we expect that to be? So we're looking for d theta dt, specifically when the man is 15 feet away from the closest point on the path. So when x is 15, okay? And what do you expect for d theta dt to be? Well, I can see here that as this guy moves along, the angle is going to get bigger and bigger, so I expect this d theta dt to also be positive. So that's a way to kind of mentally check my answer at the end. Not a complete check, but a good one. So remember that the tangent of theta equals the opposite over adjacent, in this case x over y, or x over 20. We don't have to put y here because we know the light is not going to change. It's always going to be 20 feet from the path. So I get the tangent of theta equals x over 20. To me, it's easier to solve this for x, so I don't have any fractions, so I get x equals 20 tangent theta. Again, once I have this equation that's relating the two concepts, in this case the distance along the path and the angle, then I differentiate both sides with respect to time. dx dt, one thing we didn't say is what we're looking for. Oh yes, we did. We're looking for d theta dt, sorry. So dx dt equals 20 times the derivative of tangent. Now notice this is going to be a chain rule. We're going to do the outside, which is the tangent of the function. The derivative of tangent is secant squared theta, and then the derivative of theta is d theta dt, right, with respect to time. Okay? So we don't know, actually we do know, when we know what dx dt is. That's been given to us. 20 is a constant. We're looking for the secant. Now remember that secant equals, what does secant equal? 1 over cosine. So this is equal to 1, or hypotenuse over adjacent. So hypotenuse over adjacent. So remember that x is 15. Here y, or the other side, is 20. So we can calculate the hypotenuse, 15 squared, because this is the point we're looking at when x is 15. 15 squared plus 20 squared, and then take the square root of that, and we would get that the hypotenuse is equal to 25. 15, 20, 25, using Pythagorean's theorem. And then that leaves us d theta dt. Okay? Oh, look, I've got some more up there, sorry. I guess I could have plugged those in while I'm talking. That might have helped you see some of these parts better. Okay, I didn't realize I had all those values up there. So x is 15 is given in the problem, dx dt is given in the problem, and I do think it's a good idea. And if this is 15 and this is 20, by Pythagorean's theorem, this is 25. So now I can label all my parts. Dx dt given. The secant we can figure out from this problem, again, is the hypotenuse over adjacent. It's 1 over the cosine, so it's the opposite of that, adjacent over hypotenuse. So I get 25 over 20 squared, because it's secant squared, and then d theta dt, which is what I'm looking for. So now I can solve this equation. It's all numerical at this point, very little algebra, and I get 0.128 rads per second. Okay. All right. So there were 3 good problems. I do want to remind you, where we go, that there are some videos for, I think, all of these examples in your electronic text. They may have explained this problem in a different way, and that may work better for you. So if this is still challenging to you, or you're not quite getting it from what I'm doing, go into the text and look at the video. Hopefully there are good videos and will help you understand the concept. I think related rates is a great concept in calculus to really understand what's going on and understand how these rates of change are kind of understood conceptually within the ideas of the problem. All right, so remember, drawings definitely help. If possible, make a drawing. Then work through the word problem and find and label the diagrams with what's given. If you don't have a diagram, at least label the parts using variables that are representative of the picture or of the concepts, V for volume, R for radius, etc. Don't always use X and Y. It is foolish to do that because your brain likes patterns, your brain likes organization, and it gets that R equals radius. If you make X equal radius and Y equal volume, at the end you're going to be like, wait, which was which, etc. Use things that are connected to the problem. This will help you conceptually, and it will also help you avoid errors. So look for what's given and what's unknown. The unknown is the question. There may be some other values in there, like we saw that we had to solve using Pythagorean theorem in a couple of the examples. Look for numerical values and then write them as variables, right? Then find an equation. How are the given and the unknown related? What's the formula or equation? These will all be simple things. You'll see a lot of Pythagorean theorems. You might see some geometric equations like we saw with the volume of a sphere. Then differentiate each side with respect to time, making sure that you're using implicit differentiation or the chain rule. Plug in the values that are given or that you calculated, and then solve that for your unknown quantity.